All right, so today we're going to look at our last two transformations of sine and cosine, which are your stretches, okay, horizontal stretch or compression, and our vertical stretch and compressions. All right, so we're going to start out with the vertical. All right, so the height of a sine or a cosine wave, that's called the amplitude. All right, so if you imagine a sine or cosine wave, and you measure the distance from this center line to its highest point, that's the amplitude. Should also be symmetrical if you measure the distance from the center line to the lowest point. Okay, it should be the same. Right, and since the amplitude is a height, what kind of number does height always have to be? Yeah, it always has to be a positive number. All right, so when we talk about the amplitude of a sine or a cosine function, it's never negative. Okay, and the way that an amplitude change looks is when we put a number in front of the sine or cosine function, and we're multiplying. Right, so an example is 2 sine x. That's an example of a amplitude change. Okay? And I'll explain whether it's going to make it taller or shorter in a little bit. Okay? Or we could also have y equals -3 cosine x. Okay? In this one, there's actually two things happening. The 3 is going to do something to the height. Does anybody remember what a negative does? Yep. Tom. Yeah, it's going to cause it to flip. We'll figure out whether it's going to be over the y or x-axis in a second. So for either one of these functions, if I just ask you, find the amplitude, you don't have to graph it. All you have to do is look at the number in front and take the absolute value of it. Okay, that's your amplitude. Now, if we're going to graph it, the negative makes a difference. Okay, when we sketch it, that negative is going to cause a flip. But if all we're looking for is absolute value, that negative doesn't make a difference. Right, so what would be the amplitude of this function? 2 sine x. 2. How about the amplitude of -3 cosine x? 3. What if I got rid of the negative? It's still 3. Okay? Negative has no effect on the amplitude, just has an effect when you sketch it. Causes a flip. Okay, and as I said before, amplitude is always positive. Right, so an amplitude change, that's going to stretch or compress the graph along the y-axis. Okay, what do you think is going to happen here? If I put a 2 in front, you think that's going to stretch it, make it bigger, or is it going to compress it? Stretch it, it does. Okay? Any vertical transformations do exactly what you would expect. Okay? It's only the horizontal ones that do the opposite. Right, so let's graph. Let's get rid of these. Let's try sine of x and 2 sine of x. Okay? If I don't put an operation in here, what's it going to do with 2 and sine x? It's going to multiply. That's exactly what it's going to do. All right, so here's my original. And there's 2 sine x. Right, so it does stretch it out a little bit. Right? What's the original highest and lowest y values for sine? 1 and -1. If you put a 2 in front, what do you think that becomes? 2 to -2. Okay, it stretches it, it goes twice as high and twice as low. All right, so these problems you don't have to graph. Okay, and you'll have a few like this on the test. Just find the amplitude.
Would it just be 3 -3?
Well, if it asks for the range is -3 to 3. But the amplitude is just a single number, 3. Just the absolute value of what's in front. Okay, what about the amplitude here? 4/3. Okay, let's look at some of these other numbers. We should know what all these are doing at this point. What's that +6 doing?
Vertical shift.
That's a vertical shift up 6. That doesn't change the height. And what about +π/2? Nope, that's not a stretch. That's a shift. Yeah, that's a phase shift. Okay, it's shifting it π/2 or 90 degrees to the left.
We said 6 is a vertical shift, right?
What's that?
6 is a vertical shift.
6 is a shift up. Yep. Has no effect on what they're asking here. Okay, if all they want to know is the amplitude, focus on the absolute value of what's in front. Okay, and how about -2 sine x? 2. Okay, so again, negative, no effect on the amplitude, but it will have an effect when we sketch. Okay, so any questions on finding amplitude? All right, so next thing we're going to do is graph it. Okay, and basically we're going to do it just like we did yesterday. We're going to start with those original tables, and either the x's are going to change or the y's are going to change. Okay, what do you think is going to happen for an amplitude change? Is it going to change the x values or the y values?
Y.
Yeah, it's going to change the y's. Okay, so basically, let's put this down. Right, so basically what we're going to do is we're going to stretch and compress it along the y-axis. Right, so if you just imagine you're kind of following that point, all that point does is move up or move down. There's no left or right movement. Right? And based on the slider I was just dragging, what do you think the effect would be on the sound of stretching and compressing?
When it gets shorter, it gets lower.
This one's not going to change the pitch.
So it could be volume.
It's going to change the volume. All right.
Says-
So if we turn it down like that, you don't hear it that well. And then we turn it up and it gets louder. Okay. So the effect there is on the volume. We are going to talk about the pitch or the frequency next. Right, so for this one, nice and easy. All your x's stay the same. Okay, we like when the x's stay the same because those are the ones with pi. We don't have to do any of that common denominator stuff. Okay, and to find the new y's, it's pretty straightforward. Take all the old y values and multiply by the number in front. Notice here I didn't say take absolute value. You don't take the absolute value when you're graphing. Because if it's negative, that negative is going to cause something else to happen. Okay, so whatever the number is in front, just use it the way it is.
So what if you have -2 sine x minus 4?
Well, we're going to get tomorrow to doing multiple transformations. We're actually not going to get to that today. But there is a certain order you have to do it in. You have to do one before the other. Okay, if you've been using the same letters I've used all week, you might notice I use C. C is going to be the third thing you do. Okay, for phase shift, I think I use the letter A because that's the first thing you do. But yeah, good question. But we'll get to it tomorrow. Okay, any other questions? Yep.
So we're multiplying the y's by the absolute value of C?
No, not the absolute value, just C.
Just C?
Yep. Because if C is negative, the negative is going to cause something else to happen. Okay. And we'll do one with a negative in a second. All right. So let's try graphing 3 cosine x. All right. So first thing we'll do, make our table. And what kind of transformation is this one? Okay.
Oh, actually, it's the same y change.
Yep, we're going to change the y's, and Are we shifting up and down, or are we stretching up and down?
And
Which one? Stretching or shifting?
stretching.
Stretching, yeah. So this is going to stretch. It's going to cause the graph to get taller, which would be like a louder sound. Okay, since we're going to change the y's, that means all the x's stay the same. Okay, hopefully these are, at this point, starting to get a little bit more familiar. Memorizing those is a good idea. Okay, and Amanda, what are my original y values for cosine?
It was 0, 1, 0, -1, 0.
Okay, those are y values, but those are for sine. Those are still important to know. But, yep,
I think I did 1, 0, 1, 0, 1.
1, 0, negative 1,
1.
then 0, then 1. Okay, so cosine starts at its highest, comes down to 0, hits its lowest, and then back up to 1. All right, and let me put those off to the side. And now, what am I going to do with all these y values? Multiply by whatever the number is in front. If it's a negative, use the negative. If it's a positive, use the positive. Okay? Multiply everything by 3. And those are our 5 points for 3 cosine x. Okay, any questions on getting those coordinates? All right, so now we're going to graph it. What's the highest and lowest I need to go? Yeah, so what I'm going to do is I'm going to mark that 3 and mark that -3. Okay, I'm just going to scale my axes like that so I don't have to draw in more lines. Okay, that's going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. I think the best way to probably label this is below the graph, so that way when you sketch, you don't draw through your labels. All right, so we're at 3, 0, -3, 0, back to 3. Okay, and remember as you sketch it, everything here is a smooth curve. Okay, there's no sharp turns. So just try to sketch it like that. And that's it. That's our graph of 3 cosine x. Right. Now, what's nice about changing the scale on your axes, let's say I wanted you to graph 7 cosine x. Okay. I could do just 2 things to make this the graph of 7 cosine x. Make that a 7. Make that a -7. Now, this is the graph of 7 cosine x. Goes up to 7, down to -7. So as we do these problems, you might say, well, all your cosine graphs look the same. And they're probably going to today, because I'm going to change my scale all the time. Okay? I'm just going to put my scale whatever I need to, highest and lowest values. Okay, so any questions on that? If you don't want to change your scale, that's fine. But keep in mind, if you're going to use graph paper and you've got to go up to like 7 units, you need to go up 7 and down 7. So you're going to need like 14 blocks of graph paper to do that. I think scaling your axes is easier. All right, 1/2 sine x. Right, who can tell me what's overall going to happen here? If you compared sine x to the one we're about to draw. What's going to be the difference?
Maybe half the size, like half the height. I mean.
It's going to be half the amplitude. Yeah. What is the amplitude here? 1/2. Yep. All right. So since it's going to change the height, those are my y's. Keep all your x's the same. Derek, what are my x values for sine?
0, pi divided by 2, pi, 3 pi divided by 3.
Great. Okay, and my y values, those are the ones Amanda gave us. a minute ago. 0, 1, 0, negative 1, 0. Okay, and Brendan, I'm going to take all these values and do what? Multiply by 1/2. Good. So you get 0, 1/2, 0, negative 1/2, back to 0. Okay. Questions on the table? All right, so this time we've got some choices. If you want to keep this as 1 and negative 1, you can, and draw in a mark for 1/2 and negative 1/2, or just do your scale like this. That's fine too. Okay, but whatever you do, make sure you write your labels on the test. Okay, don't forget that. All right, and let's make our sketch. So 0, 1/2, 0, negative 1/2, 0. Okay, would this be a louder sound or softer sound? Softer, quieter. Yep. Okay. Questions on that? All right, so we'll do one more example that falls into the category of an amplitude change, but little different. What's the amplitude of this function?
Negative. I mean, 1.
1. Okay, if you want to imagine there's a 1 right there, you can. So is this really going to change the amplitude? No. The original one has an amplitude of 1. This has an amplitude of 1. We're not really changing the amplitude, but this negative is going to do something. What's the negative going to do?
Flip it.
It's going to flip it. Okay, negative causes a reflection. Right, so I'm going to go through the same steps. Except now I'm just going to multiply all my y's by negative 1. Right, Matt, could you tell me what I would get if I take all my y values and multiply them by negative 1 for cosine?
Negative 1.
Yep.
0, 1, 0, negative.
Yes. Perfect. Okay, so those are my y values. Okay, so let's sketch it and see which axis it looks like it flipped over. Anybody have a guess before we sketch it? Yeah, it's going to flip over.
I was going to say the y-axis.
This one's going to be over the x.
Oh.
Right? So instead of being kind of an N shape, it's going to become more of a U shape. All right?
All right.
So just label these. And let's graph our points. So negative 1, 0, 1, 0, negative 1. All right, so normally it would look something like, let's see, it would look like this. Okay, so green would be the original, and now the black is the new graph.
Just because it was a negative 1, right?
Yep, that's all the negative did, is it caused it to flip. All right, so if I just showed you a graph on paper, you might not be able to tell how I transformed it. Okay. So if, let's say I graph sine of x and negative sine x. What's another way I could get that same picture without doing a flip? That's what I did here. Just flipped it.
Put it both.
You could shift it to the left or right.
Yeah, you wouldn't be able to tell the difference if I did this or if I did this. Okay, let's see if this works. Those two graphs look exactly the same, but one of them is really a phase shift, and one of them was a flip. All right, so sometimes there's more than one way to get a picture you're looking for. All right, so we've done the shifting horizontally and vertically. We've done the stretching vertically. Okay, our last transformation is stretching horizontally. All right, so when we stretch or compress horizontally, we're changing the period. Okay, we're changing the amount of time it takes for the function to go through all its values. What's the normal period of sine and cosine if we don't change it? Yep.
360 degrees.
360 degrees or 2 pi radians. Right, well, now we can shorten that, or we could lengthen it. Okay, and a period change looks like this. It's sine a number times x, okay? Or cosine a number times x. Now, in the last one, we used multiplication. We're also using multiplication here, but what's the difference?
It's going to be in the bench.
It's got to be in the parentheses. Okay, so that's the key with a period change. You're multiplying, but the number is in parentheses. Okay, there's no particular reason why we're going to do this, but we're only going to consider examples where b is positive. So you're not going to have to worry about flipping over the x-axis.
Is that all the time or just today?
That's going to be all the time. Yeah. Again, in math in general, there's no rule that says you can't have a negative for b. Just for what we're studying, we're not going to. Okay, so period change is going to stretch and compress the graph along the x-axis. So what do you think if I put in a really big number for b? If I did something like 8x. That's a big number. Do you think it's going to make the graph bigger, or do you think it's going to compress it? It does. It compresses it. Okay, all your horizontal transformations do the opposite of what you would think. Big numbers, the bigger the number, the more you compress it. Small numbers, like 1/3, 1/2, 1/4, small numbers make the graph bigger. Okay, so you just have to remember that. Numbers bigger than 1 cause it to compress. Small numbers between 0 and 1, we're never going to go below 0, cause it to stretch. All right, so what do you think the effect would be on the sound here? Stretching and compressing horizontally.
Will that make it change pitch?
That's going to change the pitch. All right, so this is a sound at 1240 hertz. Okay, we might say that it's, what's it? Yeah, might say it's kind of high pitch, but in terms of what we can hear, it's not really high pitch at all. So if we go up a little bit in frequency, okay, we'll play something up around 4,000 hertz. Okay, so it's getting a little higher. But anybody that couldn't hear that, yeah, it's pretty easy to hear. Okay, let's try something up around 9,000. Okay, you still hear it?
Yeah.
All right. Let's try 12,000.
Oh my gosh, turn it off.
You still hear it? Okay, now some people might start to lose the hearing in this part. All right, so we'll play it. Okay, anybody that couldn't hear that? Yeah, somebody lost it. See, I think I kind of lost it in that range. Okay, sometimes if you turn it up a little, now I could hear it. I could just barely hear it. Could you hear it?
Yeah.
No. All
I
right.
can hear it a little bit.
It's around 15,000. Some people have lost it.
Dude, that looks cool.
I definitely can't hear it at that
I
point.
can hear it a little bit.
And then if you go all the way to 20,000, that's almost impossible for people to hear. That'd be perfect hearing.
Dog whistle,
But generally, that's the higher you go. Usually, younger people can hear that better. I had a teacher in here a couple years ago that couldn't even hear it at that.
Was it this far?
Couldn't hear it. What's that? Oh, no, they retired. So as you get older, you lose the high frequencies.
Last if it was this far ago.
Okay, and then on the lower end, okay, I can't generate low frequencies really well. You'd really need a good subwoofer for that, but okay, that's a low pitch. But if I go, let's see if I can just bring it up a little bit. All right, so this sound, that weird sound you hear, that's like my speaker. That's like static or something. We can't hear 12 hertz. That's below what we can really hear. If I bring it up to about here, I think you'll hear it.
It's like
Now,
static.
let's bring it up a little bit. You'd feel it if you had, if you could put your hand right near the speaker. Hear that really low sound.
Got a good bass in the car.
So
Just so.
around 30 hertz, that's probably the low end of what you can hear.
Windows down, blast your
All right. So any questions on those different frequencies? Okay, what you can hear, what the effect is when you stretch and compress. All right. Okay. So as we stretch and compress it, okay, we're changing the amount of time it takes to go through one full cycle. Okay. What we want to be able to do is measure what's the distance to go from one full cycle. Okay. How wide is that period?
What is it? B is less than 1 unit? I didn't catch that.
And that's the formula we're going to use to find the period. Okay, so it's normally 2 pi, but if we put in b, we're going to take 2 pi divided by b, and that will tell you the new period. Okay, so if b is less than 1, it causes it to stretch. If b is more than 1, it will compress. Right, so just like we did with the amplitude, let's just practice finding the period. Okay, so my formula is T equals.
Is that how it would be written on the test time period?
Yep, find the period, yep. Now, what's B in this problem? 2. Okay, B is 2. B is not the period. B is part of the fraction that's going to help you find the period. It's the denominator. But B by itself is not the period. Okay, a lot of people make that mistake and they say, oh, the period's 2. Nope. 2 is just the denominator.
2 pi over 2.
So the period is 2 pi over 2, or just pi. So compared to the original, did this period get bigger or smaller? It got smaller.
How do you know?
What's the original size? 2 pi. This is 1 pi. Okay, 1 pi is smaller than 2 pi. All right, so this graph would be compressed. All right, let's try this one. Okay, what's my fraction to find the period?
1/3.
Well, 1/3 part of it, but that's not the whole thing.
Probably 2 pi over 1/3.
2 pi, which I'm going to make a fraction, so 2 pi over 1/3. Okay, how do we do that? Nope, you don't need a common denominator.
Should be reciprocal?
Yep, just take the top and multiply by the reciprocal of the bottom. Okay, so what's the period here? 6 pi. So is this longer or shorter? Stretched, it's a lot longer. It's triple the length it would normally be. Okay, so now this graph is going to look very stretched out. Okay, it's going to look more like that. No, not like that. Like that. Okay, it's been stretched out. Okay, how about this one? What's my period here? Yeah. What's going to happen is it's 2 pi over b. So this is actually the first time where if we graph one like this, the pi cancel out, and our x-axis could be nice numbers. None of the pi over 2 is pi, 3 pi over 2. This is the only time that's ever happened. Okay. And how about the period here?
I mean, 2 pi over 3.
2 pi over 3. Okay, if this was a multiple choice question on the test, I would definitely put 3 as a choice for the period. Okay, but 3 is just the denominator. This 2 in front, what's that doing? Vertical, change in the amplitude. How about this plus 2 at the end?
Shift.
Shift. That's a vertical shift. Neither one of those numbers have anything to do with the period. Okay, just the 3. Okay, so any questions on finding the period? All right, so last thing we got to do, just like all the other ones, is graph them. All right, so period change. Okay, just imagine you're focusing on a single point. What's changing as we stretch and compress? X's or Y's? Yeah, the X's. We're moving left and right. So if the X's are going to change, the Y's stay the same. Okay, and to get our new X values, okay, you're going to take all the old X values and divide them by B. Now, sometimes it might be easier to think of that a little differently. We did this earlier. If I divide by 1/3, that's the same as what? Multiplying by 3. All right? So dividing by B is the same as multiplying by the reciprocal of B, which is 1 over B. All right? So whether you want to divide by 3 or, divide by 1/3 or multiply by 3, that's going to be the same thing. All right? It just might be easier when we have to divide a fraction by a fraction as thinking of multiplying by the reciprocal. That's all I'm saying here. All right? So take all the original X values and divide by B. Okay, when B isn't a fraction, that's how I generally do it. But when B is a fraction, we might want to think of it as multiplying by the reciprocal. All right. All right, so we know that this is a period change because we're multiplying inside parentheses. So Emily, which column here stays the same? The Y's. 0, 1, 0, -1, 0. Now we're going to take all these X values and we're going to divide all of those by what? John? Yeah, we're going to divide every one of them by a half.
Or we multiply by 2.
Or the other way to think of it is just double everything. In this case, I think it's easier to think of it as doubling everything. Right? So let's double all of these and see what we get. Okay, so the first one,
0.
and that's generally going to happen a lot. If you take 0 and you double it, triple it, take half of it, 0 pretty much always stays 0. Now the other ones are going to change. Okay, what do we get if we double pi over 2? Pi. If we double pi, 2 pi. Next one, 3 pi. And the last one, 4 pi. Okay, so those are my X values. All right, what I'm going to do, I'm going to scale my x-axis using those values. So that's 0, pi, 2 pi, 3 pi, 4 pi. That's x, that's y. For these, the highest is 1, lowest is -1. All right, so we got 0, 1, 0, -1, back to 0. Okay, now you might say, well, wait, that doesn't look like we stretched it at all. How come it doesn't look that way? I changed my scale. Okay? 4 pi would normally be way down, because we'd have 0, pi over 2 pi, 3 pi over 2, 2 pi, and we'd have to keep going. Okay, but if you don't want to have to label that many lines on the grid, just change your scale. Okay, questions on that one? All right, cosine 2x. Again, period change. Okay, so what stays the same? Y's. Okay, my y's stay the same. And Tyler, what are my y's for cosine?
1, 0, -1, 0, 1.
All right. And now we're going to take all of our x's. And who can tell me what I'm going to do to all these?
Multiply by 1/2.
Yeah, you could think of it as multiply by 1/2 or divide by 2. Same thing. So basically just take half of all those numbers. So we can get 0. Okay, what's my next one? Pi over 4. Next one? Pi over 2.
And just be pi.
Well, pretend like you're multiplying by 1/2. So what would you get?
3 over 3
pi over 4.
3 pi over 4. Yep, 3 pi over 4 is half of 3 pi over 2. And then 2 pi? Pi. Right? That's it. That's our table. Okay. I'm going to scale my x-axis using those numbers. So I've got 0, pi over 4. Since I didn't jump over 0, I don't have that weird thing where I'm skipping. Okay, that's not going to happen here. Pi over 2, 3 pi over 4, and pi. Right, and graph your points. So let's see. 1, 0, -1, 0, 1. Okay, questions on that one? All right, let's try our last one. Okay, it kind of looks like a messy number in front of x, pi over 3. But this problem actually works out very nice. Okay, in fact, our labeling is going to be the nicest it's ever been for any problem we've done. Okay, y's stay the same. Okay, we've got those from the last problem. All right, what am I going to divide each x value by here? I'm going to divide by pi over 3, which is the same as multiplying by 3 over pi. Okay, the first one is 0. 0 times 3 over pi is 0. Okay, next one is pi over 2. So pi over 2 times 3 over pi. What happens there?
3 over 9. Pi cancels
The pi cancels out.
You said 3 over.
And in the top we have 3, in the bottom we have 2, which is, let's do it as a decimal, 1.5. Okay, let's do one more just to see the pattern. So I've got pi. What am I going to multiply by?
5 times. Right, 3 over 9.
3 over pi. Okay, what's going to happen? Pi's cancel and we get 3. So what's the gap between the x values? 1.5 each time. So let's just go by the gap. Okay, the next one. And the last one. 6. So this is an example where I'm going to label my x-axis, and I'm just going to go by ones. 0, 1, 2, 3, 4, 5. Let's put in one more. 6. And technically, if I'm going to go by ones, you don't need to label it. Okay, if you don't label, I'm always going to assume you're using ones. Right, and graph our points. So we're at 1, okay, 1.5, we're at 0, -1, 4.5, back to 0, back to 1. Okay, questions on that? All right, so last thing we'll do is just look at a couple different things we can do with sound frequencies. Okay, if we have time, maybe at the end of the week, whatever we don't do today, we can play with some sound stuff some more. But one thing I want to show you guys is what's called an Lrad. Okay, look at a little 60-second video on it. Has anybody ever heard of this? Now, Rad, you've heard of it? What do you know about it?
The military uses it to like capacity people.
Yeah, it's basically like, imagine like a spotlight. Okay, if you've got a spotlight, it only lights up a very small area of a person on stage. Well, this is like a spotlight for sound. Okay, it's a very special speaker. It sends the sound in one direction, but people behind the speaker and off to the sides of the speaker would hardly hear anything. Okay? In this room, you'd hear it because it would echo off all the walls. But if you were outside, only where you're aiming the speaker is where people would hear it. Right? So we'll look at a little clip and see how they can use sound frequencies as a or less violent weapon. It can still damage your hearing, but it's a less violent weapon than even tear gas or things like that. Okay? Pretty good to disperse a crowd. Okay, that's where they use it a lot. Okay, so let's look at that.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. Lrad, the long-range acoustic device.
A wave of the future.
A high-tech tool developed by the military.
A high-tech sonic weapon.
Long-range acoustic device, or an Lrad.
The long-range acoustic device, or Lrad, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the Lrad is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now, barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The Lrad's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks, like put your hands on your head, or lie flat on the ground, or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the Lrad has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, Lrad, the long-range acoustic device.
Right, I don't know if you saw it on the back of the Lrad, but it kind of looked like there was a little diagram. Anybody see that? It's like red, green, and yellow. Let me see if I can just find it. It was right at the end. I saw it right there. My guess is that that diagram is probably showing where the sound is most effective. So green is probably like behind the speaker. You're not going to be affected. Directly off to the sides, it's yellow, so you'd hear it, but wouldn't be that loud. And then in the red zone, that's where it's really projecting the sound, mostly in front of the speaker. So you heard that sound that they did for the Lrad. Okay, a little different than the kind of sounds I've been generating. I have that frequency, but we're not going to play it that loud. Okay, so that's that Lrad frequency. Okay, a few thousand times louder, directed right at you. Probably a sound you want to get away from. Okay, but there's a couple things happening there. Okay, it looks kind of like a sine wave, but it's almost pulsating. Right? You kind of hear this. Maybe it's the volume going up and down a little. Maybe two sounds playing at the same time. And that idea of multiple frequencies at the same time is something we can look at too. All right, so let me show you this program again. Turn it up a little bit, not that loud. And let me play something around like 1200 hertz. Okay, so that's 1200. Now, watch what happens if I play 1201 and 1200 at the same time. Everybody hear that effect? That kind of, almost like it's getting louder and softer. And the further apart those two frequencies get, kind of the faster that sound starts to pulsate. And this idea of using two frequencies at the same time is used quite a bit. Does anybody know something really, really popular you probably use every day, where you have multiple frequencies being played at the same time?
Cell phone.
Yeah, a telephone. Okay, cell phone, wall phone, any kind of phone. All right? And specifically what that's called is dual tone multi-frequency, DTMF. Right? And that's how your phones work. Right? So every button that you press, make it a little bigger, is a combination of two frequencies just played at the same time.
Phones.
All right, so as I was saying, every frequency on the phone is just a combination of two different frequencies at the same time. So let's say you wanted to generate the sound for 1. Okay, a 1 is 1209 and 697 played at the same time. Okay, let me play them separate first. Okay, that's one of them. That doesn't really sound like you're pressing anything. There's 697. And now if we put the two together, you get that sound that we kind of hear when you're pressing a button. Okay? And what you can do with that is if your phone hears that sound, or cell phone, wall phone, it'll think you're pressing the buttons. Right? So what I'm going to do is I'm going to call my voicemail. It's going to say press 4 to enter your personal options. So you can change your greeting and all that stuff. Well, instead of pressing 4, I'm going to generate the frequency for it, and it'll think I pressed it. And then it's going to say press star to exit, and then I think I got to press star one more time, and then it should exit and say goodbye. Okay, but I'm not going to press any of the buttons. All right, so it does have to be quiet because I'm kind of far from the speaker, and I do need to turn it up a little bit. That should be good. All right, and let me just get the frequency ready. It's 1209 and 770. All right, so let's try and see if we can get this to work.
Main menu. To listen to your messages, press 1. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. Personal options. To turn notifications on or off, press 1. To change administrative options, press 2. For greetings or recorded names, press 3. To change notification options, press 4. To exit, press star. You have 4 saved messages. Main menu. To listen to your message,
Okay, so just by generating the right frequencies, the phone thinks you're pressing the buttons. And besides just the buttons on your phone, I want to see if you guys recognize this. This is 440 hertz, 480 hertz played at the same time.
That's the dial tone.
Not the dial tone, but that's the ringtone. But everything on the phone, the busy signal, dial tone, ringtone, they're all two frequencies played at the same time. So with a phone like the one I have on the wall, I could just hold it up to the speaker, and if I could generate the sounds fast enough, I could make a call without pressing any buttons. All right, so this idea of frequencies, it's used quite a bit. Okay, tomorrow, if we have time, I'll show you guys some uses with music. If not, I'll show you after the test on Friday. Okay, your homework tonight is going to be those 8 problems. Okay, and I do have those on a worksheet, which I will pass out right now.